So now we get to the virial equation of state, so another type of equation of state. And the virial equation of state is really useful because we can use this idea of compression factor to assist us in the virial equation of state. Okay, so I'm going to go ahead and write it down. It goes as P Vm equals to molar volume RT. And then I'm going to write this up in the corner, right, just so you remember, P standard Vm equals Z RT. So this was another way of writing the compression factor. So you can see where we're going with this already, right? And I'm going to drop the standard notations here because we are drafting up a new equation of state that's just going to describe whatever the state of this equation is, okay? So PVM equals RT, so you can kind of start to see some similarities, okay? And now times the quantity, 1 plus capital B divided by Vm plus capital C divided by Vm squared plus so on and so forth. So if we wanted another term, it would be D divided by Vm cubed, okay? And so this number 1 here, this is what we call the, let's change colors. This is the first virial coefficient, okay? This B term is the second, C is the third. I'm going to actually clear up some room for myself here. Ooh, oh, that's good. Okay. Yes, second. And of course, if we wanted a fourth or fifth or sixth or seventh, right, this is an expansion of powers, then we recognize it would be like 1 over Vm cubed, and D would be the fourth coefficient. The fifth coefficient would be E over Vm to the fourth power, if we needed that. But of course, in these expansions of powers, we only put as many of those terms as we need based on the precision we're trying to achieve. Okay? So let's rearrange this a little bit. And if I divide this out, if I say PVM divided by RT, that's going to be 1 plus B over Vm plus C over Vm squared, et cetera, et cetera, et cetera. And now if you compare these two expressions, okay, and I rearrange this, then I recognize all of this is another way of writing the compression factor Z. Okay, so let's write that out. Okay, so now I can say Z equals 1 plus, and I'm going to do something different here with this Vm. I'm going to remind you now that this Vm, the observed molar volume, is just RT over P without these standard notations, okay? We're going to make sure really try not to confuse us with all this differing notation, okay? So this molar volume, right, this is our observed molar volume at whatever the pressure and temperature are, okay? So now instead of writing this as 1 plus B over Vm, I can actually write this as 1 plus P times B divided by RT. So I got that because this is 1 over Vm. 1 over Vm is P over RT, so P over RT times B. Okay? And then, of course, the next term is going to be plus P squared C over RT squared. Okay? And now what becomes useful with this allows me to think about Z as a function of P and T. Of course, here I have Z as a function of Vm, right? But this is the whole idea of these equations of state, right? Being able to write these in terms of whatever states, whatever variables, rather, we want, okay? And so if we do some analysis on this, okay, If we were to say, for example, dz by dp, so what is the dependence of the compression factor on pressure, dz by dp, right? Then we would get, whatever derivative this is, right? So we recognize all of these are constants. So I'm just going to write this as b prime because we recognize here that the pressure would drop out. So then I would just have b over rt. I'm just going to write that as b prime, like call it a new constant. And it's a new constant without a pressure dependence. And then now this term, right, is going to be 2p c prime, and I'm just going to also write c prime because I recognize that c over rt squared will be another constant if we're just interested in dz dp at constant t. Okay. And then of course, more and more terms. And as it turns out, when there's a special case, when dz dp equals 0, so when all these terms converge to 0, we have an ideal gas, okay? Or rather, when dz dp approaches 0, when it becomes very close to 0. That's the description of an ideal gas, which makes sense if you think about it, right? If the compression factor has no bearing on the pressure, that's saying there's no interactions, right? There's no attraction or repulsion if dz dp equals 0, or if it's very, very close to 0. Okay? And so I'll give you an example of this. I'll draw a graph right here, assuming I have enough room. And I'm going to draw this graph. This is going to look a little goofy, but here I've got z on this axis and p on this axis. And this line that I'm drawing here is not the 0 line, rather it's the z equals 1 line. Just go with me here. This is, z equals 1, okay, which we know is the ideal line, right? And there are 3 temperatures I'm going to highlight. There's one where the curve, let me make a different color here. Okay. So 3 different temperatures. At a high temperature, compression factor is going to increase like this. So I'll say, I'll just write high T. Okay. At a low temperature, and also consequently low pressure, Z will be less than 1. Okay, we'll write low T. Right? Keep in mind, right, this region right here, this is the low pressure region. This whole curve describes a low temperature. So this is if I'm just doing Z as a function of P and specifying, some constant temperature. Right? So under low pressure, the temperature is also sufficiently low enough here that it makes attraction possible, right? This is the region of Z less than 1, okay? Z less than 1 here, Z greater than 1 here. And then finally, there's a very special temperature. It's called the Boyle temperature. That's not like the boiling temperature, rather it's called the Boyle temperature, named for Boyle himself. And as it turns out, the Boyle temperature is a special case. I'm going to keep going on this with more slides here. I know I'm getting a little full on the slide. So the Boyle temperature is specifically when this term B equals 0. Okay? Because when this term B equals 0, obviously this term drops out. So there's still this 2pc dependence, okay? And that's why what happens at the Boyle temperature, it's this kind of temperature where over, a low to modest pressure range, the Z stays as 1, but eventually as the pressure starts getting high enough, this term will dominate and take off, and the gas is no longer ideal, okay? So let's keep going. Okay, so here is a summary of all that. So this is obviously a much better looking graph than what I just drew. The Boyle temp, some higher temp and some lower temp. And what I want you to keep in mind, this compression factor, if this line is like 1.00, under like most modest temperature and pressure ranges, this is not a big difference in this compression factor. So this line right here might be like 0.99 and 0.98 and 1.01 and 1.02, right? We're hardly ever going to see compression factors that are like 1.5 or 2.0, right? We're not going to compress a gas like by a factor of 2. We might compress a gas by like 1% or 2%, okay? Or we might expand that gas by 1% or 2%. So, so it's not reasonable to see these compression factors go up by these giant factors, okay? And so